So our next topic is vascular physiology. We're going to cover 5 different topics here, and I think this is an excellent topic because everything just makes sense. Our body is a wonderful thing. So first we're going to do a little equations though. So first we're going to look at flow rate. So what is flow rate? Well, flow rate is the volume of blood that is passing through a blood vessel at for a certain period of time. So the key thing to know at flow rate is that at steady state, the flow rate is constant. Okay, what this means that the rate of which blood is flowing through arteries is going to be the exact same amount of rate of blood flowing through the capillaries. If you think about it, it has to make sense that way. If it didn't, then you'd be having a buildup of blood in one area, and you'd be running out of blood in another, and it just wouldn't work. So a steady state flow rate is constant. And the definition, the equation for this is velocity times cross-sectional area. Okay, so this is constant. And this makes sense too. So velocity is just how fast the blood is going, and the cross-sectional area is telling you how much blood is in a certain is in each space. And when we're looking at cross-sectional area, remember we're looking at the total cross-sectional area for example, all the capillaries. So even though each individual capillary is a very small cross-sectional area, in total they actually have the highest cross-sectional area. So let's say for capillaries, in comparison to everybody else, they have higher cross-sectional area. But remember that the flow rate must be constant for the, let's say, capillaries compared to the veins. So in comparison, if the capillaries have a higher area, then the velocity must be lower in order for this equation to remain the same, because flow rate must be constant. So that is one important thing. The next thing we're going to look at is compliance. So what exactly is compliance? Compliance is just how stretchy something is. How stretchy the lungs can be compliant. We can measure compliance. For blood vessels, we can measure compliance. So how much they can distend. Okay. And distend for a given amount of pressure change. So distension is basically measured by change in volume, and then obviously we said it's change in pressure. So higher compliance means it stretches more. I sometimes had some difficulty remembering which one was on top. Was it the V on top? Was it the P on top? Just remember that this equation basically works so that the higher compliance means higher distension, more distension, which means higher change in volume. So I'm going to give you some numbers. So what if we say we have a change of delta P of 10, and we have it, and then thus the volume will change by 100 milliliters. Okay. If we use the correct equation, we're going to get 100 over 10 equals to 10. If we goof and we mix it up and we say, okay, compliance is P over V, then our equation will be 10 over 100. And this is a lot smaller than 10. You see, this number is a lot smaller. So this is obviously the incorrect equation. So that's how you can remember which way is which for compliance. This is an important concept, so remember that. Next, we're going to look at flow again. So an equation for it is change in pressure equals to flow times resistance. And the way I write it this way, the reason why I write it this way is because this mirrors the physics equation, Ohm's law, which is V equals to IR. So V is voltage. Voltage is it's a potential, is an energy potential difference. Okay, and if you think about it, pressure is changes in pressure gradients are also potential differences. And you would know this if you've ever been hit by like a high pressure stream of water from a hose. There's a lot of energy in there. So again, voltage is also an energy gradient, and then the I, remember, that's the electrical current, so that's the flow of electrons passing through something, okay? And then R, again, is resistance. So you see it's a complete mirror. So that just helps you remember how it works, how this equation goes. And the important part is when we rearrange it to look at flow. When we rearrange it, we get the pressure gradient over resistance. And this is a super important equation. It's simple. You may just gloss over it, but I want to emphasize how important this is. This equation tells us everything. Okay, it tells us exactly how blood will move throughout the body. Blood will move depending on the pressure gradient. So it will go from high pressure to low pressure. And the other way that blood will be affected is through the resistance. Okay. And then we're going to look at resistance real quick. There's an equation for it. where resistance equals to 8 times viscosity. This is the symbol for viscosity times length over pi r to the fourth. Okay, so quick thing on viscosity. Viscosity is basically it's pretty much dependent on hematocrit. Hematocrit HCT. Hematocrit is the proportion of red blood cells in the blood. So remember, blood has a lot of other things. It has plasma, it has white blood cells. But hematocrit is dependent on basically the concentration of red blood cells. So the more red blood cells in the blood, the thicker it's going to be, and thus the more viscous. And the more viscous your blood is, the higher the resistance. If you ever just think about honey. Honey is very viscous, and it doesn't flow very well because it has high resistance. The other key thing to look at is the radius here. Remember the radius here, and then the other thing is it's exponentially to the fourth. So radius plays a disproportionate role on the resistance. It's very important. Remember, the changes in our radius can be, our blood vessels can change the radius. Remember, we have sympathetic stimulation. What is that going to do to our blood vessels? It's going to cause vasoconstriction. So that's going to be a decrease in the radius. So if you decrease the radius, then you're dividing by a smaller number, so your resistance is going to go up, and it's going to go up by a factor of 4. Okay, so vasoconstriction will increase your resistance greatly and decrease blood flow. Another very relevant concept is for atherosclerosis and coronary artery disease, where you have atherosclerotic plaques. Let's see, so this is our blood vessel. So we have a nice little radius here, okay? And then we have a plaque here that can block everything up. Now you see the radius is much lower. So the radius goes down, the radius goes down a lot. Resistance goes up even more, okay? Goes up to the fourth power. And then if we go back to this flow equation, which we said was super important, if we increase the resistance, flow is going to go down. So when you have that plaque, you're going to decrease blood flow to that area. Very important. So that's it for equations. Again, this is a super important equation. Resistance, you kind of want to know this equation. It's a little complicated, but you kind of want to know it. Compliance, remember, just it has to make sense. Higher compliance means more distensibility, so higher change in volume. So that's how you remember which one's on top. And then flow rate is our last equation. So next topic is natriuretic peptides. This is also I think it's a beautiful concept. So basically, there's two natriuretic peptides. The first one is the atrionatriuretic peptide. Guess what? It's from the atria cells. And it's released from the atria cells with atrial distension. So you get distension when there's increased volume, so volume overload. So there's more blood in the atria, it's going to stretch it out. And what the atrionatriuretic peptide does is it counteracts that volume overload. So it's a counterbalance to the volume overload. And it's going to lower your blood pressure by natriuresis, so excretion of sodium, and diuresis, which is excretion of water from the kidney, okay? Remember that sodium helps you retain water. So when you get rid of sodium and water, you're getting rid of a lot of volume. The last thing it's going to do peripheral vasodilation, okay? So all of these factors are going to lead to decreased blood pressure and decreased volume. The next one is brain natriuretic peptide, which happens to be a misnomer. It's not from the brain. It's made from the ventricular cells. And it's, in short, it's BNP. Again, same idea. It's pretty much the same as atrionatriuretic peptide, except for it's released from the ventricles. It's released due to distension, which is volume overload. Similar action, which is what? Remember, this action was natriuresis and diuresis, as well as peripheral vasodilation. And the other things to note is it has a longer half-life. And in heart failure, the key thing is heart failure is basically when your heart is failing to pump. So when it's not pumping well, you're going to have a lot of extra fluid, and that extra fluid is going to cause release of both ANP and BNP. And so BNP is a great test for heart failure because it's going to be elevated in heart failure. So our next topic is baro and chemoreceptors, and this is, again, it's very similar. It's a very beautiful concept of how we can self-regulate our body and the blood flow. So first of all, there's receptors in the aortic arch, which is right here, and then receptors in the carotid sinus. There's receptors that sense blood pressure, so those are the baroreceptors. So remember, the baro is for pressure, so remember, barometer is a measure of pressure measuring system. And then the chemoreceptors, which measure molecules in your blood, and specifically it's going to measure oxygen, carbon dioxide, and pH. Remember, these are all very related. So if you have areas of decreased blood flow, then you're gonna have those areas are gonna have decreased oxygen, or if you have decreased blood flow in general, you're gonna have decreased oxygen. And that decreased blood flow, remember that blood flow helps to get rid of all that carbon dioxide. So decreased blood flow, then the cells will have decreased oxygen. They can't get rid of the carbon dioxide because there's no blood to take it away, so carbon dioxide builds up. When carbon dioxide is kind of an acidic thing, it's in reactions and causes a decrease in pH because you get increased hydrogen ions. So this will be important. So these all transmit signals up to the medulla, okay? And it's going to do that through specific nerves. So this is the carotid sinus. It's going to transmit it through the glossopharyngeal. Do you remember what cranial nerve this was? This is cranial nerve 9. Okay, glossopharyngeal. And then the aortic receptors are going to transmit through the vagus nerve. So vagus nerve, cranial nerve, remember what it was? It was cranial nerve 10. So just remember the cranial nerve 10 goes farther down, so it's the one that goes all the way down to the aortic arch. So let's look a closer look at the baroreceptors and what happens. So what happens when there is decreased blood pressure? Well, there's going to be decreased blood pressure throughout the system, and it's going to be detected at the aortic arch and at the carotid vessels. So when the receptors sense that decreased blood pressure, they're going to decrease the rate of firing of the parasympathetic innervation. And when there's decreased parasympathetic innervation, then remember it's a balance between parasympathetic versus sympathetic. So the sympathetic is going to predominate. What's going to happen to the heart and the peripheral system? Then the heart is going to beat faster. It's going to have greater contractility, and then your peripheral system, remember, it's going to get a vasoconstriction. And all of this is going to function to increase your blood pressure and increase blood to parts of the body that you need it. So it's a beautiful thing. Decreased blood pressure causes this whole reflex system that ends up with increased blood pressure. So another test, I want to check your understanding. What happens if you massage the carotid massage? Well, what's going to happen locally at those carotid baroreceptors is going to have increased pressure locally because you're manually applying pressure. Okay. Well, that increased pressure, what's going to happen is going to increase firing of parasympathetics. Okay. And then what's going to happen? What's going to happen to your heart? Well, you're going to have decreased contractility. You're going to have decreased heart rate. What's going to happen in the peripheral system? You're going to have vasodilation. And at the end of the day, what's going to happen is you're going to get decreased blood pressure. So this is a beautiful system. Everything just makes sense. So if you honestly, you don't have to remember anything about whether the parasympathetics are activated or decreased. If you know the end goal, so if you know that you're going to sense decreased pressure, your goal is to increase blood pressure, then obviously how you're going to increase the blood pressure is you're going to get decreased parasympathetic stimulation. So it all makes a lot of sense. Finally, we have the chemoreceptors. Again, there's chemoreceptors at the carotid and the aortic chemoreceptors, carotid and aortic arch. These are termed the peripheral chemoreceptors. We term them that because they're central chemoreceptors, and those are in the brain. There's a little difference in between them. So the peripheral ones respond to changes in O2, CO2, and pH. So remember that if we have decreased blood flow, you're gonna have decreased O2. We said what happened to the CO2. Remember that goes up, and the pH goes down. So in response, these chemoreceptors are going to cause vasodilation. Okay. And what the vasodilation is going to lead to increased blood flow. So increased blood flow is going to help us reverse this and increased oxygen, get rid of all that waste products with CO2. So in central chemoreceptors, the big difference is that it does not respond to changes in O2. It only responds to changes in carbon dioxide and consequently pH, because carbon dioxide can diffuse through the blood-brain barrier. So this is very important. So when it does sense that increased CO2, that means that there's not enough blood going to the brain, so there's not enough blood getting rid of all that CO2 waste. So in response, this chemoreceptor is going to sense that increased CO2, and then it's going to cause vasodilation to cause increased blood flow to get rid of that CO2 and supply that brain with blood. This is a beautiful concept, and it all makes sense. Alright, so that's it for part 1 of our physiology. We're going to go to part 2.